Allow me to redeem myself and finish the notes properly on section 3.4 regarding concavity and the second derivative test. So where we left off, I believe, was me giving you this example. Find the intervals where f is concave up or concave down given the function 1/3 x cubed minus x. So we found first the first derivative was x squared minus 1, the second derivative was 2x, and then now using the second derivative to analyze what's happening about the function, we do something very similar to what we had done in section 3.3, and we make a table or a chart using the intervals negative infinity to 0 and 0 to infinity. We got that 0 by setting the second derivative equal to 0, and we're determining where our possible points of inflection are. So we set this equal to 0, and that's how we were able to determine that 0 is a possible point of inflection. And then plugging in test points to the second derivative, you see that anything from negative infinity to 0 gives us a negative value. Therefore, that means f is concave down on that interval. And when you substitute in a value between 0 and infinity, you get a positive outcome for the second derivative, which means f, the original function, is concave up on that interval. Alright, so think back to section 3.3 from the last Edpuzzle video. In order to find the extrema, or the maxes and mins of a function using the first derivative, we set up a table, or a chart. We set the first derivative equal to 0 to find these critical numbers, or critical points, and I'm going to summarize all this vocab later. And then we determine where the first derivative is positive and negative. Wherever the first derivative is positive, the function is increasing. Wherever the first derivative is negative, the function is decreasing. So this is old news, but I'm going to use this same example from example 1. That function was 1/3 x cubed minus x. Okay, so using that same example here, you can see where I have a change from increasing to decreasing, that's where we have a relative maximum. And where I have a change from decreasing to increasing, that's where I have a relative minimum. So we could honestly roughly sketch this thing without using our graphing calculators. So the information we just gathered previously was the concavity. This information gives us the relative extrema. So I can see at -1, I have some type of max. At +1, I have some type of min. I know the function is concave down from negative infinity until I reach 0. So I know that my function might look something like this, and then concave up from 0 until infinity. So that's just a rough sketch of the function based on the information we gathered. We have our relative extrema, and we have our concavity correctly sketched. So before, when we said 0 was a possible point of inflection, we can verify 0 is definitely a point of inflection because it changes the concavity. Okay, so then what I was rambling about trying to explain the second derivative test. This test is another way to find extrema. But instead of using the first derivative, we're using the second derivative. You might be confused by this, but I'm going to explain how we use the second derivative to verify that -1 and +1 are the maxes and mins. Here's what I really wanted to say when I had you start writing notes on the second derivative test. You can basically just throw out that page, erase it, cross it out. We're starting fresh at this point. The second derivative test, which when I say the second derivative test, I'm talking about the test for extrema. So we already know we can use the second derivative to determine the concavity. We can use this idea of concavity to also figure out the extrema of the function using the second derivative. So here are those steps. The first thing you want to do is set f prime of x equal to 0, because we just want to identify our critical points. Once you've identified those critical points, we're going to test them in the second derivative. So you take those critical points and plug them in to the second derivative. Finally, here's the results of the second derivative test. If the second derivative is negative when you plug in the values of the critical points, then that means we have a max. Now this should make sense, because what you're really saying is at that critical point, the second derivative is negative, which tells us that at that point, the function is concave down. So if the function is concave down there, and it was a critical point, it must mean that that point is a max. Now, conversely, if the second derivative at a critical point is positive, then that must be a minimum, because at that point the function would be concave up. Using the exact same function that we've been talking about, f of x equals 1/3 x cubed minus x, we already know that when we set the first derivative equal to 0, we get positive and negative 1. So those are our critical points. If we substitute those numbers into the second derivative, f double prime of negative 1 gives me negative 2. So since this is a negative value, I know for a fact that at negative 1, I have a max. And then I also see when I substitute in my other critical number, positive 1, I get positive 2. So since I get a positive outcome, I know for a fact that I have a min at positive 1. So that's how the second derivative test works to find extrema. But let's jump right back into this business of discussing concavity and using the second derivative to do that. So in this example, it says find any inflection points and discuss the concavity. When it says discuss, you're just going to determine the intervals where it's concave up and where it's concave down. So this is a very, very, very basic example. We're going to do a couple more interesting ones in a moment. But in this scenario, again, you want to find the second derivative. So let's start by finding the first derivative. F prime of x is 4x cubed. F double prime of x is 12x squared. So remember, the first step is to set the second derivative equal to 0 when we're trying to discuss the concavity and determine any possible points of inflection. So I'm going to take 12x squared and set that equal to 0. In this case, yet again, kind of boring, x is 0 is a possible point of inflection. So a PPOI, possible point of inflection. Not sure yet. Might be, might not be. So that is the point that I'm going to use to break up my interval when I set up my chart. So my chart should be from negative infinity to 0, and then from 0 to infinity. Now I'm going to pick a test point between negative infinity and 0, so typically negative 1, pretty easy. Substitute that in. And for the second derivative, negative 1 gives me a negative result. Oh wait, actually my bad, it's squared. Positive result. Cool. And then plugging in positive 1, we get, again for f double prime, a positive result, because it is 12x squared. Okay, so what does this mean for f? Well, for my original function, I know that it is concave up from negative infinity all the way to positive infinity, because for both answers I got a positive second derivative. So this function is concave up from negative infinity to positive infinity, and there's no points of inflection. So 0 is not a point of inflection. So there are no points of inflection if it's not changing concavity at all. It is strictly concave up. So no points of inflection here. Let's find any inflection points and discuss the concavity of this function, x squared plus 1 over x squared minus 4. So we know in order to do that, we have to find the second derivative. First derivative, we have to use quotient rule. I would recommend pausing the video and trying it on your own, but I'm going to go ahead and give you the answer. So the first derivative is equal to negative 10x, after you simplify the numerator, over x squared minus 4 squared. Okay, so for the second derivative, we'd have to use quotient rule yet again. And I'm going to give you the answer, so if you want to work it out, I would pause the video and try it. I'm giving you the answer in factored form in the numerator, and I'm using a technique from algebra called factoring by grouping to do so. So I get negative 10 times the quantity of x plus 2 times the quantity of x minus 2 times the quantity of negative 3x to the second power minus 4 all over x squared minus 4 to the fourth power. Alright, so if you need to review how to do that factoring in the numerator after you get the second derivative, I can help you out with that later. But this is in fact the second derivative. And why am I writing it in factored form? Well, this is going to help me enormously when I'm trying to set this second derivative equal to 0 and solve for x. Okay, so when we do that, you should notice that the only values of x that will give us 0 in this scenario are positive and negative 2. So those are going to be my possible points of inflection. So now I'm going to use those points of possible points of inflection to set up my sign chart. So from negative infinity to negative 2, negative 2 to positive 2, positive 2 to positive infinity, and let's see what's going on here. So when I substitute in a value between negative infinity to negative 2 for the second derivative, I end up getting a positive outcome. When I substitute a value between negative 2 and 2, I get a negative outcome. And when I substitute a value in from 2 to infinity, I get a positive outcome. So how do we interpret these results? Well, this means that my original function that we started with, f, is concave up from the interval negative infinity to negative 2, is concave down on the interval from negative 2 to 2, and is concave up from 2 to infinity. So those possible points of inflection are definite points of inflection here. So we do have these two POIs because I switch from concave up to concave down, and then I switch again from concave down to concave up. So since we have that switch happening, concave up to concave down, I would have a point of inflection there at negative 2. Concave down back to concave up, I would have a point of inflection at positive 2. So our POIs are at positive and negative 2. Alright, so we're going to stop there for this lesson. Hope you enjoyed.